So you can see here the nitration of toluene gives you orthonitrotoluene and para-nitrotoluene. Okay, so you can say the CH3 group is orthopara directing. CH3 group is ortho-para directing. Look at this molecule. Bromobenzene is sulfonated. Again, you get the same type of substitution. Bromine here, SO3H. That is the group which is introduced on sulfonation. You can have bromine here and SO3H here. So this is called orthobromosulfonic benzene sulfonic acid, ortho and para. Ortho and para benzene sulfonic acid. Okay, so that is the sulfonation product. Now look here. Now look here. Nitration of nitrobenzene. Nitration of nitrobenzene will give you the NO2 is here and NO2 here. So this is meta-dinitrobenzene. Meta-dinitrobenzene. Okay. Meta-dinitrobenzene. And here, this, again the same bromine. You will get bromine here, plus you will get bromine here. Sorry. Bromine. So you can see here, CH3, Br, and yeah, here also Br. CH3 and Br gives you orthopara, while NO2 will give you a metaproduct. Now, like this, different groups you can classify as orthopara directing and meta directing. Okay. Now, those groups which contain lone pair of electrons, groups with lone pair of electrons, groups with lone pair of electrons groups with lone pair of electrons on the attached atom. On the attached atom. They are orthopara. Example, Br. See here, Br is attached. You have 3 lone pairs on Br. Similarly, Cl. NH2. OH. OCH3. All these groups are donating groups, electron donating groups. Similarly, you have plus I groups, plus I groups. Example CS3. What is the meaning of plus I? Here is you have a carbon, you have 3 hydrogen, and you have the benzene here. Now see, the electron flow is towards the carbon on this bond, on this bond, and this bond. So electrons will flow from the hydrogen by inductive effect towards this carbon. And what is the net effect of this? There will be a donation of electron by inductive effect into this benzene ring also. Okay, so that will increase the electron density of the benzene ring. So something which increases, okay, groups which increase the electron density of the benzene ring. Will activate the benzene ring and they are orthopara directing. They are orthopara directing. Okay. So this is what is the what is meant by orthopara. Now why are they orthopara directing? Why are these groups orthopara directing? Okay. So we have Padma again. Why are these orthopara directing? Why are they orthopara directing? What is the answer? The answer is one word answer is resonance. That's a one word answer. Let me expand it. Let me expand. We will take voice as a group. OH. So this is the answer. If you are given this question, why is OH group? Why are they? Why is the OH group orthopara directing? See here, you write on the top resonance, and then you draw the structure. Draw all the resonance structures of phenol. I think we have done it before. Okay, I will just draw one of them. This is the resonance structure. You can see the lone pair of electron is contributed to IC in the benzene ring at the ortho position. The lone pair is the lone pair is contributed to the ortho position. So ortho position become rich in electron. Okay, next it will go to the meta position, para position. Next it will go to the again the second ortho position. So you have to draw all resonance structures. So draw the resonance structures, and then what explanation you can give? Ortho and para position, positions are electron rich, and hence electrophiles attack there. Like that. Right? Similarly, if you look at the other groups, what are the other groups? NO2. Let's take NO2. We have already studied the whole structure of NO2 group. You have two lone pairs here. Plus. See that? Then you have CN. Look at CN. CN. Nitrogen is having a lone pair. But see this by inductive effect, the electrons are attracted more towards nitrogen. That means this is delta positive. NO2 is already delta positive. This is already delta positive. But it's already positive. Okay. Then you have SO3H. SO3H group. Again, see here delta negative, and delta negative. Why? Because by inductive effect, sulfur is less is more electropositive than oxygen. Again, electropositive onto this side. So all the electrons are moving away from the sulfur. So this becomes sulfur. The sulfur is delta positive. Okay. Then a carboxylic acid group. CW1 OH. Again, see here. This is delta negative. This also is delta negative. This is delta positive. Okay. Similarly, you have a carbonyl group. CH3. All the compounds containing carbonyl group. Here also delta negative and delta positive. So what you have to do is you draw the structure of the molecule. See here. Now if you are asked, is this group orthopara-directed? We have drawn the structure. Good. Now what do? Look at the polarity of each atom. You have the oxygen with delta negative. This oxygen is also delta negative. That means, yeah, one sec. So what you have to do is both are delta negative. What did I write? The name of the paper. So both are delta negative, and therefore you have a carbon which is delta positive. So once now that means the attached atom to the benzene ring, the atom attached to the benzene ring is carrying a partial positive charge. That means electrons will be flowing away from the nucleus, from the benzene ring. That is, the electrons are attracted towards this carbon. That means the electron density is reduced. So, when the atom of the group attached to the benzene ring carries a delta positive charge. Electrons move out of the ring, reducing its electron density. So when electron density is reduced, hence it is deactivated. Hence, it is deactivated. Again, you have to draw the resonance structure. If you draw the resonance structure of this group, I should put all these groups here. I got there, so I can write the resonance structure. See this. You can draw the resonance structure, all the resonance structures of this molecule. So that is the answer why this is ortho meta directing. See here, you can draw the remaining resonance structures. Oh, sorry. You can draw the remaining resonance structure. Minus here. And you have a plus here. So orthopara is electron deficient. So electrophile cannot attack here. But what about the meta position? There is no change in electron density. Meta position is relatively electron rich. Okay, so from resonance structure, orthopara positions orthopara carbons are electron deficient compared to meta. Position. Hence, electrophiles will attack relatively richer meta position. metacarbon. So this is so that is why these groups are metadirectic. So which are the groups? Look at these groups. These are metadirectic. And don't forget to draw all these structures when you are given the groups. Don't forget to write the structures. Okay. Now we will consider a few reactions. Now I can give you any group, and you should be able to tell me whether it is orthopara directing and metadirecting. And in this also you can see there are certain groups which are weak orthopara directing, certain groups which are strong orthopara directing. Okay, that also you can very easily say. Say for example, look here. Look at this group. See this. And see this. Uh, here. You can see here, this is very strongly orthopara directing. Sorry, metadirecting. But here, you have a lone pair of electrons, which will increase electron density of this carbon. Okay, and therefore this is weakly metadirecting. Weakly metadirecting. Here, these electrons are more closely towards nitrogen, and this is strongly metadirecting. So there are certain groups which are strongly meta and strongly weakly meta. Similarly, you can classify the orthopara also in a very similar fashion. Example, chlorine. Okay, chlorine, they are weakly orthopara directing. Chlorine, bromine, iodine. They are weak orthopara directing groups. While OH, OCH3, they are very strong orthopara directing. Strong orthopara directing. Why is that? Because these halogens are more electronegative. Halogens are more electronegative and hence inductive effect. Inductive effect is stronger. In halogens compared to mesomeric effect. No, compared to mesomeric, compared to other elements, not compared to mesomeric effect. Sorry for that. Compared to that of other elements like oxygen, nitrogen. Nitrogen and oxygen. Okay. So, and therefore what happens is you have an electron withdrawing inductive effect and electron donating mesomeric effect. Okay. So slight excess is there for the mesomeric effect. That is why we call it as a weak orthopara-directing group. So I can write mesomeric effect of Cl or halogen is partially nullified. It is partially nullified by the inductive by the inductive effect minus I effect of the halogen. So that will be slightly orthopara-directing. Okay. Now let's look at some of the reactions of this effect of the effects. See here, if I take phenol and react with bromine in water, you will get not a bromophenol, it gives you tribromophenol. See how much 3 bromine get attached in the orthopara group, orthopara position. And see, this is a white solid. And the reaction nearly goes to 100%. Nearly to 100%. And therefore, you can use this, and it's very fast reaction, very fast. You know, precipitation, this forms a precipitate, it's a white solid, insoluble in water. Okay, so this will get precipitated out. The tribromo derivative, the tribromo product will be precipitated out. And since it is almost 100%, you can use this reaction for the analysis of phenol. This reaction can be used for the purpose of analyzing phenol. Very similarly, you have, suppose you have an H2 group here, NH2. If you have NH2 group, this bromination will give you tribromoanidine. Tribromoanidine. Okay, so that is the power of this particular group. These two are very, very highly orthopara-directing, highly activating the benzene ring, and because of that, 3 of the bromine atoms get attached to it. Okay, other compounds, let's look at other compounds. Other reactions we have already done. Suppose I take benzoic acid, COOH, and react with nitrate, SNO3. Look at this carbon, this is a carbonyl compound, and it is delta positive here, and therefore this will be COOH and NO2 here. NO2. Is it clear? So these are the different reactions of that is disubstitution on benzene ring. Okay, and the explanation why they are orthopara-directing or why they are meta-directing. Okay, so remember you have to draw the resonance structure for explaining the orthopara and meta-directing effects. Okay. So what next we have to take up is aromaticity. That we'll take up tomorrow. Tomorrow is Friday. Yeah, that's right. Aromaticity. Okay. I think if I remember, okay, last week's class I missed. Yeah, last week I missed a class, right? Last Friday. Yeah. So I think this Saturday also we'll take up for half an hour as usual. So please remind me of that for that, right? Okay. So that is so the remaining part we'll take tomorrow. Okay. Thank you. I had 10 people today. I have taken attendance. I think I have written it here. I will just repeat it. I hope all the people are there. I got Aisha, Dilna, Fasna, Jadida, Musina, Arsha, Najma, Noora, Rinshina, Padwa, and Najia. Anybody else? Please tell your name. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Somebody is already gone.